Today, we are very happy to have invited Professor Raymond Chewing Wong from our Computer Science and Engineering Department of the Hong Kong University of Science and Technology. He's currently the Associate Head of the department. He has been in a range of administrative positions. He was an Associate Director of the Data Science and Technology Program, Director of the Risk Management and Business Intelligence Program, and also Director of the Computer Engineering Program. Raymond received his Bachelor of Science, MPhil, and PhD degrees in Computer Science and Engineering from the Chinese University of Hong Kong some time ago. He also worked in a range of professional positions, which I will not mention. His research area include database and data mining. With that, let's invite Raymond.
Okay. Thank you, Hans, for invitation. Let me start the talk. Okay. Today the topic. Okay, you can hear, right? Hello. Yes. Okay. Okay. Today the presentation topic is big data analytics on big spatial database. I'm Raymond Wong from the Hong Kong University of Science and Technology. Let's see a case study how to analyze big data. Here is a data set. Okay, in Singapore. In Singapore. Okay. In Singapore, each taxi is equipped with a sensor. We know the path and trajectory of each taxi based on this sensor. So, okay, yes, okay. We can collect the location of each taxi every second. There's a lot of points generated. Okay, let's see. During the rainy day, okay, it's difficult for us to find a taxi in Singapore. Maybe all of you have some reason in your mind, okay, why we could not find taxi easily during the rainy day in Singapore. Maybe the first reason in your mind may think that, okay, oh, taxis are too slow on the road and they would like to avoid accident. This is what you think, so that we may not find taxi easily. However, okay, in the big data, in the data, we find that the GPS location of taxi are often on the roadside. Okay, they didn't move. Okay, they just parked on the roadside, and only few cars are moving on the road. Okay, so this contradicts with our possible reason one. And maybe we also have another reason, okay, in our mind, okay, maybe we thought that, okay, there's a lot of people would like to use taxi, okay, during the rainy day. And then there's a higher demand, okay, from the customer side. However, based on the data, we also know that this is not true. The data during this period, the taxi income dropped significantly during the rainy day. And based on this data, we know something wrong, okay? And in fact, let me tell you, the fact is that a Singapore law says that high penalty was imposed for car accident during the rainy day. So this is what we find in the big data. And now we discuss a case study using the spatial data. Let us see more applications. Here, I think all of you also use a lot of mobile apps, including Facebook, WeChat, and so on. And all of them are mobile-based spatial app. We have location-based app more than 500. And let me go through my research one by one using this framework. Okay, what do location-based apps do? Okay, first of all, okay, I use these features. Search nearby. Okay, what is this? Okay, search nearby is very simple. We want to find something nearby to some location. And let's see this example. Yep, open rice and so on. You can see that, okay, at the top we have the restaurant, and then the second, the middle one, okay, we have the HKUST. We want to search for some search nearby restaurant near to UST. And the other one is Foursquare, also common in United States. We want to find a place near you. And also Goala, and also we want to find some spot near to my current location. And these are all my previous work related to search nearby, published at that time, except top K nearest except top K nearest keyword search in large network, hypersphere dominance and optimal approach, collective spatial keyword queries, a distant owner-driven approach, and the last one, efficient method for maximizing biochromatic reverse nearest label. All are published in the top-tier conferences, okay, in my field. And today we will not talk about this one. We just gone through some high level one. And now go to the second features, spatial crowdsourcing. This one, okay, what's this? Okay, crowdsourcing is a platform where people can post tasks and some other people can perform tasks. And each task is associated with a location. Workers need to go to the location physically in order to perform the task. And for example, taking a video, okay, at Times Square at New York. You can see that this is an app 3 mission, and we can post a new task there, and the location may be UST campus, and we'd like to take a photo of 5 birds. This is the task. And the other things also common in United States is called local hands. We can also say outdoor home, for example, slow removal, leaf removal, we post the task, and some people will pick the task. An air tasker, and then you can also pick up and deliver and post tasks there. And these are 2 previous work related to spatial crowdsourcing related to me on optimal worst case matching, on efficient spatial matching. Now go to the third one, trace tracking, which is also one feature in location-based apps. This can record the trace of a movement. For example, the app will sample the position of the trace periodically. You can see that Mass Plus, okay, you can see that this guy doing a hiking on a mountain, we can have a trace recorded in the app. And also Nike Plus, also the trace. And this one, Runkeeper, is used by me when I run near to my home. And then this can capture the kilometer I run and also the calorie I burned at that time. And this also are 2 previous work related to this, trajectory simplification or minimizing the direction-based error, direction preserving trajectory simplification. And now go to the last one, which is the focus today, shortest distance. And finding shortest distance, what's this? I think this is very simple to you. Since all of you may use Google Map, Baidu Map, or Apple Map, and so on, we just have a starting location and the destination location. We want to find the shortest path. And here I have a lot of work on this domain. Path Advisor, a multi-dimensional campus map tool for shortest path, distant oracle on terrain surface, and new lower and upper bound for shortest distance query on terrains, finding shortest path on terrain by queuing 2 birds with 1 stone, hub doubling label indexing for point-to-point distance querying on scale 3 networks, terrain toolkit, a multi-dimensional tool for terrain data, IS label and independent set-based labeling scheme for point-to-point distance querying, and last one, finding shortest path on land surface. Today, okay, in this talk, we would like to focus on one particular shortest distance query, which is shortest distance on the terrain, which is a new direction. Here, this is my work related to the shortest distance on terrain. Okay, let's see the first one. This is, I want to highlight this one, finding shortest path on terrain by killing 2 birds with 1 stone. This paper, the presentation outline is as follows. First of all, we'll talk about the introduction of the paper, and then we will go through 2 problems, problem 1 and problem 2, finding lower bound and surface simplification, and then empirical study and conclusion. Now go to the introduction. Finding shortest path on terrain. You can see that in this figure, we have a terrain with some mountain. We have the starting point here, and also the destination point here. Suppose that we need to walk here from here to here, okay? We have many different possible paths. The red color one, path 1, the blue color one, path 2, and the yellow color, path 3. One of them is the shortest one. And there's a lot of application in this domain, terrain surface and geodesic distance. Application 1 to application 5. Application 1, geographic information system, GIS. Application 2, computer graphics and vision. Application 3, scientific data 3D modeling. Application 4, 3D virtual game, and recently Facebook announced Metaverse is also related to this work. Application 5, spatial data mining. And for application 1, you can see that we have the 3-dimensional data geographic information system. Based on this, we can find something, for example, shortest path and some other related spatial queries. Application 2 in computer graphics, this kind of things is also happen in some 3D model like this. And also application 3, scientific data 3D model. They also use 3D model inside, and this kind of work can also be applied to this 3D model. Application 4, as I mentioned, this is related to metaverse, and actually this means 3D location-based virtual game. Okay, inside that you can use the methodology in this framework inside. And application 5, spatial data mining, we can also consider the inner and inter-cluster distance. And in the mountain view, okay, the geographic distance is a good metrics in this framework. So let's go to our introduction. Existing spatial query on terrain rely on computing efficient lower and upper bound on the shortest distance for pruning. And this is our major study in this paper. We understand that we need to find the shortest distance. However, most existing spatial query, they also consider how to compute lower and upper bound for shorter distance so that the algorithm can be faster. So this can be done faster. In this paper, we would like to improve the quality of lower bound for more effective operation, okay, in this algorithm. Maybe some people here are not in computer science. What I want to say is that if we compute the shorter distance at the beginning, but it's computing shorter distance is too expensive, too costly. Usually the technique is to use the lower and upper bound so that we have a faster algorithm. And then in our paper, we improve this quality, okay, of this lower bound. And then our paper can speed up the computation of lower and upper bound for efficient computation. Let me go to the details, and then you know what I mean by lower bound and upper bound. Here is finding shortest path on terrain. And then we have two mountains, okay, just like a shape. Usually, okay, in the computer science, we represent this in some form. For example, we call triangular irregular network T model like this, okay? We have a lot of triangle to represent these two mountains. Okay, now let's focus on these two mountains. Suppose that we have a source and also we have a destination. If we want to find a shortest surface path, okay, a shortest path on this surface, okay, and then there's a state-of-the-art algorithm called Chen and Han algorithm. However, in computer science, we say the time complexity. The time complexity of computing this state-of-the-art algorithm is big O n squared, where n is the total number of vertices in the model. What is the meaning of vertices? Okay, you can see that each triangle have a corner. Okay, this corner and this corner and this corner. This corner correspond to the vertices. So how many corners are there? N squared. And then actually this is very expensive, okay, in computation. And now let's see, this is the red color denote the shortest surface distance from source to destination. And there's a lot of shortest surface path paper on terrain in the literature. Surface k-nearest labor query, surface range query, surface reverse nearest labor query, finding shortest path. Although I don't go through the details with you, but according to the name, you also understand we want to find some nearest labor. We want to find something within an area or a region and so on. And this is the reverse version of this labor and so on. So what I want to say here is that there's a lot of existing spatial query. They also have a component for finding the shortest path or shortest distance. So what we will talk about is very fundamental, can influence the whole field. And then, since computing the shortest path is very expensive, most of this algorithm need to find a lower bound and upper bound, as I mentioned before, okay, of shorter distance, which computation cost is much cheaper, much faster than computing the exact shorter distance and path. So this is the reason why we need to study to improve the lower bound, okay? Now let's see this example. As I mentioned, we want to find the shortest surface path from source to T, and then we have this figure. And now let me give you some literature review so that you understand what is the meaning of lower bound. Here we know that the red color one, the total length of the red color lines correspond to the shortest distance from source to destination. And the lower bound is in the literature, okay, in the literature, it's not mine, okay, it's just a direct Euclidean distance. Okay, you can see that the green color one is a lower bound, okay, of the red color one, which means that the length of this green color one must be smaller than or equal to the length of the red color one. Okay, this is the common technique in the literature. And you also understand that just 2 points, we just compute the Euclidean distance. So the computation cost is very low, very fast. And also one common upper bound of shortest distance used in the literature is as follows. They would like to find the shortest network distance. That is the shortest distance on the graph. What's that? Okay. Now take a look on the left-hand side. We can see a lot of black color edges or line, and then this is just like a graph. And then what I want to say is that the shortest network distance is that the path, okay, is just based on the edges and the line here. They will not go through the triangle. They just go along the edges of the triangle, okay? So you can see that the blue color one is the shortest network distance, just restricted on the edges of the triangles, okay? I think by geometry, you understand that the white color one, we can jump here, which is much shorter than this blue color one. So we understand that intuitively, the length of the blue color one must be larger than the length of the red color one. So this is the upper bound, okay? In the literature, they use lower bound and upper bound to do some operation to speed up the computation. And also since this one is very, only involve a few edges, so the computation cost is also cheap, okay? Although this is much larger than the previous one, the lower bound, but it's also faster than the computing the red color one, okay? And this low computation cost of a standard algorithm called the Dijkstra algorithm. And this lower and upper bound are commonly ignored in the literature for pruning, okay, which can speed up the algorithm. And however, the weaknesses I want to highlight is that, okay, the existing lower bound is too loose. It does not use any information about the terrain. You can see that the red color, the blue color one, it used the terrain structure. However, the green color one, the lower bound, didn't use any information about the terrain. This is the weaknesses of the existing algorithm. In this paper, we have the first contribution. Contribution number 1, killing 2 birds with 1 stone. I think you understand this word, okay? We do one thing and then at the same time we can do 2, okay? What is the meaning? We know that we have to compute the shortest network distance for the upper bound, the blue color one. This should be computed already. And what I want to say is that our new lower bound is just equal to this blue color one, the shortest network distance, multiplied by a constant, divide from the terrain, okay, divide from the triangles, okay. This is our contribution 1. So when we compute the blue color one, immediately we have the length and then multiply by a constant. Then we obtain a better lower bound, okay, better than this green color one. And so what we want to say is that there's no additional computation cost except the multiplication with a constant is introduced. So the problem in this paper is that we want to find a lower bound. We want to find a lower bound of the shortest surface distance, which is equal to the blue color one, the shortest network distance, multiplied by a constant divided by the terrain. Okay, this has been discussed before. And now I want to highlight this one. For upper bound and lower bound, our contribution also need to compute the shortened network distance, okay, based on this graph. Okay, we just know we pass through all the edges. However, we want to say something like this, okay? Although computing the shortened network distance on large graph 3, this is 3, okay, is very fast, it can be more attractive to compute the lower and upper bound even more quickly. In this paper, we will have contribution 2. We call surface simplification. What's that? We want to simplify the surface of the terrain so that the number of triangles will be smaller and thus the graph is smaller. Since the graph is smaller, then when we compute the network distance based on this smaller graph, which will be faster. This is the major idea. Based on this smaller graph, computing the shorter network distance is faster. At the same time, the lower and upper bound computed based on this smaller graph is close to the lower upper bound computed based on the original graph. This is our idea. Now let's see the visual illustration. Originally, we have many triangles, and after the simplification, we have fewer triangles like this. This is what we did in this paper. And then now we want to highlight what we mean by simplify. Okay, let's see. Okay, we want to quantify this, what we mean by simplify. Okay, this is the process. We will introduce a user parameter, omega, which is a real number, at least 1, denoting how much we can simplify. For example, omega is set to 1, then the smaller graph gives the same lower and upper bound as the original graph, okay? If omega is larger, then the tightness of the band, the lower bound and upper bound will be sacrificed. Okay, sacrifice means that it's not that tight. Okay, I will illustrate more in the next few slides. Okay, now let's see. Here is lower bound. Okay, we understand that. Okay, now we have the graph G, which is this one. We have a smaller graph G pi, which is the bottom one. And then based on this, we can also compute the blue color network distance like what we have seen before. On the original graph, the upper graph, we can compute the lower bound, okay, L, and also the lower bound computed based on the smaller graph, okay, L y tau. What I want to say is that, okay, what we compute the estimated lower bound on the smaller graph must be smaller than or equal to the original lower bound, okay. This one makes sense since the lower bound is looser, so this must be smaller than the original lower bound, okay. This is the case for lower bound. For the upper bound, the case is reversed. Let's see. We also have the same notation. U is the upper bound based on the original graph upper part. Y tau U is the upper bound computed based on the smaller graph G pi, okay, which is the smaller one. And now this is the upper bound. And the estimated lower upper bound based on the smaller graph must be looser. So the estimated upper bound must be larger than or equal to the original upper bound. Since this is looser than the original upper bound, okay, this also makes sense here. And if you understand these two inequality, then let me introduce more criteria. Since L pi is smaller than the original low bound, if Y tau L is very, very small, for example, equal to 0, then this estimated low bound is useless, okay? So what we want to say is that even though we have a looser low bound, but it's not that too small, then we introduce another criteria on the left-hand side of this Y tau L, okay? Such that, okay, this Y tau L, our estimated lower bound on the smaller graph must be at least this one, the original lower bound divided by omega, which is our original parameter used here. So omega is equal to 1. Our estimated low bound is exactly the original low bound. Similarly, for the upper bound, we also don't want our Y tau U is very large, for example, infinity. We also have a range on it, okay? Also the same. Here we have an upper bound here, so that this estimated upper bound on the smaller graph must be smaller than or equal to the original upper bound multiplied by omega. Same as before, if omega is equal to 1, then the estimated upper bound become the original upper bound. If omega is larger, then we are looser. This is the problem. Now let's see. Problem 2. Surface simplification. We want to speed up the computation of upper bound and lower bound based on surface simplification. Given the original graph G, we want to generate a simplified graph G pi, this one, such that for any source and any destination, these two inequalities must hold, okay? This inequality and this inequality must hold. This is problem 2. Now let's go to the problem 1, okay? Problem 1, okay, let me read again. Problem 1, finding lower bound. We want to find a lower bound of the shortest surface distance, which is equal to the shortest network distance multiplied by a constant divided by derived from the terrain. And you can see that, okay, this is the red color one is the original shortest surface distance. Now let me define this angle. Each triangle, okay, has 3 angles. We call an interior angle, okay, of a triangle. Suppose that we have a notation called theta m. This theta m, okay, correspond to the minimum interior angle of a triangle in the terrain, okay, the minimum value. And then we know that this is the surface distance, and then we denote it with this notation, st. And this corresponds to the shortest surface path as we mentioned before. We also know that this is the direct Euclidean distance, the existing lower bound. And then the blue color one, okay, you know that this is the shortest network path, okay? This is defined by us, just cross on the edges, okay, denoted by this one, 3st. Okay, now let me give you the lemma or the result we find in our paper. Here is the existing result. Let me emphasize, this is existing result, okay? This one is the existing upper bound. You can see that the left-hand side, this one is the length of the shortest surface part, means the shortest surface distance, okay? And then this is upper bound by the blue color one, okay? The blue color one, the length of the shortest network path on the right-hand side. So I want to emphasize that this is the existing upper bound. And now this is our result. The left-hand side is our result, okay? Our result is that this one, the length of the blue color one, multiplied by a constant could be smaller than or equal to the red color one. So this is a lower bound than the original one. But what is lambda? Okay, let me give this to you, okay? Lambda is equal to this formula, minimum between this term 1 and term 2. Term 1 sine theta m, okay, theta m is here, divided by 2, comma, sine theta m and cosine theta m, okay? Maybe you have not much idea about this one. Let me give more detail to you. Lambda is a constant derived from the terrain. Terrain means the theta m, okay? The minimum interior angle of a triangle in the terrain. If theta m is smaller, okay, according to some equation, then we can compute that the lambda is very small, okay? You can see that if this is very small, so suppose this is 0, then the lower bound becomes useless since this is only 0, okay? However, in computation geometry, there's a concept called realistic terrain, which can maximize theta m easily. And in our experimental result, when we use this concept, theta n can be at least 45 degrees. Based on this, then lambda can be only at least 0.35, at least 0.35. So in our experimental result, our lower bound is 2.3 times much larger than the existing lower bound, which means that our lower bound is much tighter and which is more helpful. Okay. Since our lower bound is tighter compared with the existing lower bound, existing algorithm using our lower bound for pruning can be split up effectively. Okay, now go to problem 2, surface simplification. I don't go to the detail, but give a high-level idea so that you understand how we do this one. Problem 2, let me recap. Surface simplification, given the original graph, we want to generate a simplified graph G pi such that for any source and any destination, these two inequalities hold, which is related to the estimated lower bound and estimated upper bound. Okay, let's see our algorithm. Our algorithm to generate a smaller graph is as follows. First of all, we iteratively remove a vertex from the original graph and check whether the simplified graph satisfies the above two conditions. Okay, we do it again and again, and then we stop when there does not exist a vertex in tree, such that the resulting graph G pi after the removal of this vertex satisfy these two conditions. Okay, this is the major idea. There's some detailed implementation which make our process faster, okay? But you just need to understand the idea. And then we just output the smaller graph, okay? This is the idea. Now we go to the experimental result. Here we use a benchmark data set called Eagle Peak in United States. We have a lot of points, 1.3 million data points. And we use a spatial query called surface K nearest neighbor query. You can see that also have the nearest neighbor. Okay, we want to find some nearest neighbor. And this query requires to find the shortest path. Okay, these three algorithms, SF straightforward, MR3 VOR, okay, these three algorithms also solving this query, and these three query are also using shortest path query. Since they also use the upper and lower bound in their method, our proposed approach can be embedded in their original method effectively. Let's see the result. Here is the parameter. K is set to 2. K is the spatial query. We want to find two nearest neighbor, okay? This K is 2. And omega is our algorithm parameter. We set it to 1.2. So we have some, for example, 20% error and so on. And then the measurement is query time, okay? Let's see the algorithm for comparison. The original algorithm, using the original lower bound and upper bound on the original graph, okay, we denoted as SF, MR3, and VOR. Let me give more notation. Here is the original bound on the original graph, okay, same as these two algorithms. And then Our updated algorithm using our new lower bound on the original graph, okay, we also use these three algorithms. We just replace the original bound with our new bound, okay? So we have this notation, our bound on the original graph. This corresponds to our contribution 1. And then we will show the experimental result in experiment 1 to show the effectiveness of contribution 1. And then here we also have the updated algorithm using the original graph, original bound on the simplified graph, our contribution 2. Similarly, we also have these three algorithms, and then you can see we are using the original bounds on the smaller graph. Okay, so we are using this notation. Finally, okay, this one is experimental 2, contribution 2, simplified graph G. We want to show this contribution. Finally, we have the updated algorithm using our new bounds and on the smaller graph. Okay, you may guess out the notation, our bounds and the smaller graph. And this can show the effectiveness of the combination of contribution 1 and contribution 2 together. Okay, let's see the result one by one. Experimental 1, contribution 1 lower bound. Okay, let's focus on the left-hand side figure. Here we vary the K. Okay, K is the parameter related to that spatial query. K means neighbor. And here is the query time. And then you can see the legend. Okay, you can see that SF original boundary. Here, SF our boundary. Okay, you can see that the dashed line here is our contribution. The dashed line, okay, our bound, the dashed line is our bound. So roughly speaking, you can see this figure, all the dashed line, okay, are also smaller than the original algorithm, which is much faster. The major result is that after they are using our lower bound, okay, this can speed up the query time process, okay. On the right-hand side, since some detail has been skipped, okay, you may not know what is the meaning of number of candidates. You don't need to understand the right-hand side figure. Now go to experimental 2. Similarly, we want to study the contribution 2. Let's see, we also vary K and measure the query time, same notation. We have the dotted line, okay, correspond to original bound on the smaller graph. We can see that here, okay, the dotted line, okay, mostly also at the bottom, which means faster, okay, than the original method without using the simplified graph. And contribution 1 and 2, which means experiment 3, we use our bound and the smaller graph together. You can see that in this figure, where we K and measure the query time, the dotted line, okay, are also at the bottom, okay. So we have a fast query time compared with the existing algorithm using the original bound on original graph. Here, we finish the experimental result. Now go to conclusion. Here, we propose a tighter lower bound on the shortest surface distance, a fundamental operator in many spatial queries on the terrain. We also propose how to simplify the surface so that the lower and upper bound computed on this simplified surface are near to those computed on the original surface. Our method can speed up existing algorithm up to 43 times for well-known spatial queries. Okay, now we finished the first paper. Now go to the second paper, Distant Oracle on the Terrain Surface in 2017. And here is also a presentation outline. I just picked some of them for illustration due to the time limit. Also the same introduction and the algorithm I will not talk about. I just give the major idea and then go to the experiment and conclusion. Let's see introduction. Similarly, we also have the terrain surface and also geodesic distance. Similarly, okay, is it also a many triangle. You can see that we have the source, where the destination, okay, and then this is the surface path, okay, the dotted line is the surface path. This is the geodesic path, and you can see that this is direct one, like the green color one we mentioned before, the Euclidean path, okay. Here in the terrain surface, I need to introduce some concept. Vertices, as I mentioned, the corner of the triangle, the black color dot. Edges, as I mentioned, is just a line, okay, this line, and this line. The line are in the triangle. Faces means the triangle, okay, so each triangle is a face. And geodesic distance between S and T, as we mentioned, is just the length of this geodesic path. And in this paper, I would like to discuss is we would like to consider one additional concept called point of interest, okay? What's the meaning of point of interest? Point of interest is that the yellow color one, okay? Which means that the source can be on the face, okay? Not just necessarily at the bottom, at the corner of the triangle. We can at the middle on the face, okay? You can see that the white color can also on the face, okay? This is what we mentioned point of interest. And then let's see the deficiency of existing papers. These two work, okay, are computing distance on the fly. On the fly means that when given the graph, okay, on given the terrain, they will compute the shortest distance quickly, okay, without doing any pre-processing. Let's see. The exact algorithm and their running time is very, very slow, okay, for this exact algorithm, even though the approximate algorithm, which means the algorithm may return some error, also is very slow, okay? They are very slow, okay? I will show the result, how slow they are later. And also, there's some other word called approximate distance oracle. If you don't understand this word, which means that all the algorithm here pre-compute some index, okay? We call oracle, okay? Or data structure. And then based on this data structure, we can speed up the computation, okay? And the query can be faster than the previous one on the fly, since something has been pre-computed. Okay, let me give more details. This algorithm has some guarantee epsilon approximate, which means the error should be at most epsilon. Epsilon is a user specified parameter. And the major idea of this approximate distance oracle is as follows. It introduces a large number of slider points or edges. Okay, if you don't understand this word, it doesn't matter. Which means that we will add more points, more edges, okay, to this one. Okay, here we have maybe they will introduce a lot of points along this edge, a lot of more points, a lot of more points along this edge, and then based on all these points, just do add edges between all these additional vertices or points. Okay, and then this means that okay, they will have a lot of points introduced and also a lot of edges introduced in the framework. So this introduced that they have a large space since they have more points and more edges. And then since they need to introduce a lot of points and edges when they build the index, okay, build the data structure. So the building time is also very fast, is very large. And then since they didn't consider the yellow color, the point of interest, so they also have some problem. And also, I want to highlight is that there's another spatial query, as I mentioned before, k-nearest label query, reverse k-nearest label query on this topic. Now, let me talk about the contribution of this second paper. We propose a distance oracle, SE. Actually, this stands for space efficient. And we have the accuracy guarantee, which means that epsilon approximate. Epsilon is a user specified parameter, which means that our distance should be bounded by epsilon. And this is our contribution. We significantly outperform the state of the art with all these aspects. Building time, we are much faster than the existing algorithm, 1 to 2 orders of magnitude, which is very significant. Oracle size, the size of the data structure, 1 to 3 orders of magnitude smaller. And also query time, we have 2 to 3 orders of magnitude smaller than the traditional query time with the same error guarantee. Maybe you are curious about the major idea. The major idea is as follows. The major idea of our data structure indexes the approximate pairwise distances between points of interest directly, okay? And this avoids the introduction of a large amount of Steiner point and edges in the data structure. So this is the major idea. The detail will not be discussed here. If you understand this, now go to the experiment. Here we also use the one we present before, the Eagle Peak. And then we also have another data set called Bearhead and also San Francisco. These are the details of the data set. You don't need to understand. You just know that this is our data set about the terrain. We also use some machine, okay, and the programming language. And now we have 2 baseline for comparison, okay? The first baseline is SP Oracle. This is the best known existing distance oracle or data structure. And K-Algo is the faster on-the-fly algorithm. Okay, so we used the best one. This one, without using any pre-computation, the best one. This one, if there's some computation, this is the best one. We use the 2 best one for comparison. We measure the building time, okay, building the index, the size of the data structure, and also the query time. And these 2 algorithms also certify what we certify epsilon approximate distance. So the distance returned is also bounded by epsilon. Now let's see the result, okay, in San Francisco dataset. We vary the echelon, our problem parameter, and measure the building time, okay, how the time to construct the data structure, the size of the data structure, and the query time to answer the shortest query, okay. And we have our these two baseline as mentioned, SP Oracle and K Algo. This is our algorithm space efficient. Let's see the left hand side. Here the building time, you can see that this is our 9, okay. We can see that, okay, we are smaller than the baseline. And for the size, the size of the data structure, we can also smaller than this one. Let me conclude this one. The building time, okay, which is this one, and also the space consumption of our data structure is smaller than SP Oracle, okay, which means this one, the existing data structure by 1 to 2 order of magnitude. And also the space of SE is also smaller than SP Oracle, 1 to 3 times orders of magnitude in this figure. And now go to this figure, which is the query time. We are here. Let me conclude here. The query time of our space efficient algorithm is much smaller than the SP Oracle or the existing other algorithm by 2 to 3 or 5 to 7 orders of magnitude. So we have a very significant contribution. Now go to the conclusion. We propose a distant oracle on the terrain surface. It returns as long approximate distance. It significantly outperforms state-of-the-art by orders of magnitude. Now we finish these two papers. Lastly, we will also talk about a path advisor. Since you may know this kind of work, I also introduce the terrain, okay, in this path advisor. Okay, let's play the YouTube, okay, generated by my student, okay. Let's see, share computer sound.
Hi everyone, in this video, I will introduce Path Advisor. I will first introduce the technical contribution and the existing work, and show the demonstration, which includes the interface, the 2D view, bird's eye view, and the VR view.
Oh, I see. You are not share the whole. Okay.
And then you take this one.
Oh, I share the whole screen. I this one. Yeah.
No. Yeah. And then you click share screen at this one.
I think this one is okay, right?
No.
Oh.
That one.
Let's see. I think this one is okay, right? I usually use this one.
Okay.
Yeah. Let's see. Let me see the sound. Yes, okay.
In this video, I will introduce Path Advisor. I will first introduce the technical contribution and then the existing work, and show the demonstration, which includes the interface, the 2D view, bird's eye view, and the VR view. Now, let's take a look about the technical contribution first. There are two requirements that need to follow. First, the path should not be too close to the obstacle. And second, the path should not have sudden direction changes. So we have used the weighted shortest surface path algorithm to satisfy the two requirements. In details, if a face is closer to the obstacle, then the weight of a face on the floor pan is larger. And if a face is closer to the center, then the weight of this face on the floor pan is smaller. I will use two figures to illustrate. As shown on the second figure, the terrain face near the boundary has a larger weight, so I use a darker color to represent it. In this case, the path will be forced to choose the face with a smaller weight. Then, let's talk about the existing work. Some papers have used the road network to calculate the shortest path. It is also called the graph network. And some papers used the unweighted shortest surface path. And some also used the ground obstacle shortest surface path. In our work, we have used the weighted shortest surface path. Compared with other existing work, our path pulled away from the obstacle, and there is no side direction changes. Then, let's take a look about the interface, as shown on the left-hand side. This corresponds to the building. Each building will also have different floors. This is the from point and the to point. This is the legend for showing different icons on the map. This is for bird's eye view, and for VR view. This is for zoom in and zoom out. For the legend, we can enable or disable different icons on the map. And this is the suggestions. We have the mobile version for both Android and iOS. This is the help page and the About Us page. Next, let's take a look about the 2D view. You can input the source point and the destination point from the drop-down menu. For demonstration purpose, we have also add via point. Then you can click Go. This shows the shortest path from the atrium to the escalator on the ground floor, and you can take the escalator from the ground floor to the first floor. And this is the shortest path from the escalator to the lift 26 on the first floor. And you can take the lift 26 from the first floor to the third floor. And finally, this is the shortest path from the lift 26 to the room 3541 on the third floor. And the detailed direction has also been shown here, from atrium to escalator, and from escalator to lift 26. For the other two views, we will also have the same direction. We also have the distance and time, and the total estimated time. Next, let's take a look about the bird's eye view. This is the shortest path calculated using the weighted shortest service path algorithm. You can double-click the red pin to change to different floor. Then, let's take a look about the VR view. The user can use the mouse to control the direction, and the keyboard to move forward, backward, left, or right. And you can follow the blue dot line to go from the source point to the destination point. And you can click the lift door open button to open the lift door, and the lift door close button to close the lift door, and the floor button to go to the floor you want. You can click the door to open it. And you can click the door handle to open the door. Thank you. This is the end of the video.
You can see, right? Here. Yeah. Okay, we have already finished the third paper. Okay, and then this is my work about the shortest distance on terrain. And then now let me summarize. Okay, we have talked about the shortest distance just mentioned, and then I also did a search nearby spatial crowdsourcing and trace tracking. Okay, this is the Q&A session. Thank you very much.
So thank you, Raymond, for a very exciting talk. I learned a lot. I work on this area a little bit. I think sometimes we look at the app and say that's very easy, but there are a lot of science and consideration behind the calculation. I think that is very important, that we provide timely and fast solution. Any questions from the audience? Let's see whether I can see some chat. Please. Okay.
How do we figure out the graph on the surface, on the terrain surface? Because when we are finding the shortest path, is it to find the shortest path on the graph we created? And then is this path the real route
Okay, yes. Actually, what you mean is that according to some realistic, for example, surface in the world, how this surface can be mapped to the model I mentioned. For example, the T model. Okay, there's a lot of standard technique for that. Okay, one technique is that we do a grid sampling. Here we have a grid, okay, 1, 2, 3, 4, 5, with some regular distance, and then just sample all the points. And then we have all the sample points, and then based on the points and the coordinate, then we have the surface. And based on this surface, and then there's some standard technique to generate the triangle there. Yeah, yeah. And then after that, okay, you talk about some part can be walkable or not walkable. This can also be modeled in this T model. Since each triangle you can assign with a weight. And if this weight is infinity, then this is not walkable. Yeah.
Yeah, because I'm just wondering, because we apply your algorithm, so then we can get the shortest path. But is it, this is on the graph we created, but it's not on the real route, right?
Real good. Actually, this the path found on the T model can be mapped back to the realistic surface.
It's a 3D, it's
yeah.
not 2D.
Yes.
It's 3D.
Yeah.
I'm just wondering
Yeah.
how elevation is being considered. Do you consider elevation?
Elevation, yes.
So
Elevation.
how do you do that? Because typically I think about a network is 2-dimensional, right?
Yeah.
When you're 3-dimensional, how do you do the,
Yes.
the elevation?
For example, this is the mountain, and then you just think we have the satellite,
Yeah.
and then we just have some laser, and then we know that this one has some elevation
Yeah.
here, and then with some elevation and also XY coordinate. So we have all the XYZ coordinate during this process. Yeah.
So you have to think
Yeah.
about XYZ kind of shorter span.
Yeah. Yes.
Okay.
3-dimensional. Yeah.
The other question, you talk about the lower bound, upper bound. You have this ratio called 0.35, right?
Yeah.
Does it work for regular network? Can we
Yeah.
apply that
Regular network.
to
what do you
create?
mean by-
Because let's say we have a network fine grid. We know the shortest path will be bounded within this surface, right? You cannot go outside.
Yeah.
So can we apply this ratio to limit the search of the shortest path even on a road network?
Okay, I see. The technique used in this that at the first paper could not be directly applied to the structure you mentioned, but also there's some existing paper that can use another technique, okay, to boundary search. For example, some pre-computation to know, for example, what we mentioned about direct Euclidean distance, and then there are other technique in our field, landmark and so on. So that we can also have some other technique to find the lower bound and upper bound. Yeah.
Okay.
Yeah, but not the technique I introduced on terrain. Yeah.
Okay.
Yeah.
We talk to you.
Yeah.
We're interested in that. And also in the, I'm thinking about in the network that we code for street network for people walking. So what kind of resolution would be sufficient, right? So you can code a lot of small streets, or you can only code a big street. Similar to your example is a triangle, right? How big and small the triangles are. Are there any way where we can say this size of the grid is sufficient?
Yes, actually, when I do the first paper about surface simplification, we also don't know how large the triangle
Yes.
is, okay, at that moment. But after my work is published, I have a clear understanding how to set the size of the triangle. Since we have some idea what we want for this resolution, for example, the shorter distance, and then based on the contribution 2 of my paper 1, and then we just originally just high sample the density sample of the triangle, and then use the contribution to the algorithm to simplify, so that we also have the good look, okay, of the simplified surface compared with the original surface, and at the same time also satisfy with, for example, shorter distance. So
yeah, we should talk. One last look. If there's any question from the audience, please type or raise your hand. I saw the Path Advisor app, 3D, right, with VR and everything. Is that already done, open to the public?
Not actually, this is just a proof of concept,
Yeah.
and it requires a lot of manpower to do the coding for many different places. Okay, in the academic building and
Yes.
also those things. See, there's a lot of manual work inside
Yes.
there. For example, draw some edges inside, virtual edges inside,
Yes.
and also you can see there's an elevator. We can click the lift the button.
Yes,
And those
yes.
things are also very labor intensive.
But
Yeah.
what I mean is that
Yeah.
we don't want to look at the button, right? We want to know the path. The
Yes,
VR can take us.
yes.
Since Jack is here, we already have the digital twin coded. How is that we can combine digital twin and your work so that there's 3D routing? We probably don't need VR yet. The 3D routing can be implemented. Is Jack here?
Yes.
Can you
Okay,
comment on
so,
that? I think it's very exciting.
Hello, Raymond. So I think it's a very interesting demo and very interesting talk. I just want to double check the beam model or the 3D model actually is from the dual twin project,
Yes,
right?
this is all thing from what you generated, of course. Yes,
Right.
yes.
So I think I can see the synergy that we can extend this one to other parts of the dual twin project models. And what we are now facing is the connectivity between buildings, because this is the limitation of the path advisor right now, that we only have the path advisor directions within the building, but not cross the building. And this is something that we are also working on. We can talk offline and see what you would like to support, because if we can provide the B model, because our team also work on the navigation. At the same time, I think at least the B models, 3D models are ready. And if you can have the version of the path advisor in 3D, that would be interesting and great.
Yes, actually, my final year project is also doing the 3D model on path navigation. Yeah.
Okay. Yeah. So we
Yeah,
talk
I think we
offline.
can
Thank
keep
you.
the conversation going. I really like to see our campus as a 3D. But you can also do the routing up escalator, right?
Yeah.
Which is non-trivial.
It's non-trivial. It need a lot of manpower. Yeah.
Yes.
Now we are checking with the FMO to update our model. So we can pass the existing model, but later when the model is updated with the input of FMO, then we can give you the updated version of it.
Okay, thank you.
Okay, great. Anyone from the audience? Any other questions? I thought some of the competence really interesting. I don't know how you prove this sine cosine thing. It must require some work, right?
It requires a lot of mathematics.
Right? The theta m is a minimal interior angle. That requires a lot of geometry.
Yes, sure. Yeah, yeah.
But that's very exciting. Okay, anyone else? If not, no question. Okay, please go.
So I'm thinking a little bit more practical using this. So because you talked about in the team network, so we can probably add some logo places, right? Some places with the infinity weighting. Is there some way to maybe limit the steepness of the path?
Yes, yes. Actually, one of my previous work I didn't mention. Also consider the slope constraint. Slope constraint shortest path, and also this is given by the user. For example, I don't want to walk at most, for example, 30 degrees. Okay, then based on this, we have the slope constraint shortest path. Yes, this also consider in my work and also some other researchers. Yeah.
Good. I think that's all we have. Let's thank Raymond for a very exciting talk.
Okay, thank you.
Okay, I think we have the recording in case you want to revisit this seminar. You're welcome. Go to our website in GSCI. You find it. Okay, thank you.